Welcome back. In this final lecture, we're going to discuss Stokes' theorem a little bit more. And our first discussion is going to be over the interpretation of curl. Divergence can be interpreted as the amount of stuff created per unit volume at a given point. It's a form of the derivative for a vector-valued function, for a vector field. And so is the curl. But the curl has to do with rotation, not with expansion. And those are two separate concepts, right? The expansion business and the rotation business are independent of each other. And that's why we have a divergence theorem and Stokes' theorem. But they say kinds of similar things. They're both a generalization of the fundamental theorem of calculus. So if we have a vector field and we imagine a tiny disk of radius alpha centered at xyz with a boundary c alpha, and we compute the flux, the path integral, the work done by the field going around the path, that gives us the circulation around the point xyz. Now, as that shrinks down, we expect that to go to 0. But what we want to look at is the ratio of the path integral to the area. And if we look at the limit as the alpha goes to 0, that gives us the work divided by the area as alpha goes to 0. That's the curl of f at x, y, and z. In other words, a way to define the curl, well, the curl dot the normal vector, is the limit as the radius goes to 0. We divide by the area of the circle, and we take the work integral around that little circle. That's one way of defining the curl. It's a little bit less intuitive than the divergence theorem, but what we're saying is that the rotational tendency taken over the entire surface is equal to the tendency of a fluid to circulate around the boundary of the surface. So let's use Stokes' theorem to evaluate another work integral around the boundary of this surface. So this surface is a quarter circle in the xy plane, but above it is the parabola z equals x squared. The parabolic cylinder z equals x squared. So that's what we're seeing here, right? The other side of the cylinder goes up in the negative x direction. And instead of just getting the entire parabolic surface, we get the part that's above that quarter of a circle in the xy plane. Now again, if we were to parameterize this, we'd have to parameterize this curved part of the boundary, we'd have to parameterize this straight part of the boundary and this other straight part of the boundary. And we'd have to make sure that they're all oriented properly so that the unit normal vector is pointing in the right direction. So we want to, counterclockwise is viewed from above. What that means is we want the k component of the normal vector to be positive, right? If it's counterclockwise when viewed from above, that means that the normal vector is pointing up, right, in the above direction. Well, Stokes' theorem says that this integral around the boundary of the surface is equal to the flux integral over the surface of the curl of f dot n, which again we're going to express as the curl of f dot Ru cross Rv, whatever, where u and v are our parameters, whatever they happen to be in the final analysis. In this case, I think we're going to use cylindrical coordinates, or xy polar coordinates. So we need to parameterize the surface, and that includes getting the cross product of the partial derivative vectors. We need to worry about the curl of the vector field and substituting the x and the y and the z components from our parameterization of the surface. And then we need to set up our integral. So our surface is going to be the interior of the disk, not just the circle itself, so that's why it's less than or equal to. So we need to parameterize S, the surface, which I think I will do using radius and angle, and that will be our cosine theta I, which is always x, plus our sine theta j, which is our y, and then z is x squared, so r squared cosine, plus r squared cosine squared theta k, right? Z equals x squared. If we do our partial derivatives, we get cosine theta I plus sine theta j plus 2r cosine squared theta k, and the derivative with respect to theta will have minus r sine theta I plus r cosine theta j minus 2r squared cosine theta sine theta k. The cross product of those, well, the I component is going to be minus 2r squared cosine theta sine squared theta minus 2r squared cosine cubed theta. The j component will be minus 2r squared cosine squared sine plus 2r squared cosine squared sine, which thank goodness is 0, plus the k component, that's r cosine squared plus r sine squared, which is r. Well, once again, we can simplify this. We can simplify this quite a bit. In the first one, the common factor of minus 2r squared cosine theta leaves sine squared plus cosine squared, which is 1. So that is the I component. The j component is 0, and the k component is r, which makes sense that the y component of the normal vector is 0. Now we have our x and our y and our z, so now we need to find the curl of our field and substitute x, y, and z in there. I think we can probably fit that over here. Our field is xyzi plus yj plus zk. If we do our matrix, what we get is, for the I component, we get 0 minus 0, so 0i, plus for the j component, we get yz, and for the k component, we get 0 minus xz. Now, when we want to substitute our x and our y, so our x and y and z, we get that this is equal to 0i, and then we have y times z, that's r cubed sine theta cosine squared theta, j, minus x times z is r squared cosine cubed theta. The good news is, when we do the dot product of the curl of f with r cross r theta, the x component disappears because there's no x component in the curl, the y component disappears because there's no y component in the cross product, and the only thing that survives is minus r cubed cosine cubed theta, again from the r here, and the minus r squared cosine cubed from the other. One other thing to note quickly, the k component of the normal vector is positive because we're looking at positive r values. I didn't put the limits for theta and r. Since we're in the first quadrant, we're going up to pi over 2 in the theta direction and up to a in the r direction. So r is greater than or equal to 0. That is the upward pointing normal vector. So this is what we want. We just have to integrate that from 0 to a, and with respect to r, and from 0 to pi over 2 with respect to theta. Integrating cosine cubed from 0 to pi over 2, we get the Wallace formula that is just 2/3. So we get minus 2/3 integral from 0 to a of r cubed, which is a to the 4th over 4. The 2 and the 4 simplify, and we get minus a to the 4th over 6. That's it. That is the entire, that's the value of the integral. Oh dear, that should be r cubed. I apologize, which means this should be r to the 4th, which means this should be r to the fourth, r to the fourth, r to the fourth, a to the fifth over 5, which gives us negative 2a to the fifth over 15. I apologize, I missed a power of r in the curl. This is now correct. Negative 2a to the fifth over 15. So that's pretty much it. What you will need to remember is how to use these things. I will give you the summary of integration formulas from chapter 15. You still have to know how to set up the path integrals and the surface integrals and the flux integrals and the work integrals. You need to know how to set all of those up, but you don't need to remember all of the theorems. So that's it. Thank you for your time, and I hope to see you in either differential equations or linear algebra.